to Mark Thomas, who's the CEO of First Light Fusion. Mark.
Great, thank you very much. Thank you. Cool, good to see you all. Thanks. I'm representing the other side of fusion, inertial confinement fusion, if that makes sense to people. So that's a pulse process. You pulse tiny pellets of fuel with lasers or electrical pulse power, as opposed to magnetic confinement fusion, which is much more like a continuous furnace type process that was well described in the earlier presentations. So First Light, we're an Oxfordshire-based company, private fusion company, relatively small, 75 people with end-to-end capability, and we span out of Oxford University. Very IP rich. We have a unique in the world technology that's an enabler for high gain fusion, and that's our amplification technology that I'll talk about. Is dual use, so it serves both fusion and energy, fusion energy and defense, and also is now selling into the space sector. We're end-to-end capability. We do a lot of high-end modeling simulation. We're the only fusion company in the world, and there's 70 fusion companies in the world. We're the only one that has its own coding capability that's been built from the ground up, and our own AI that we've developed over the last decade or so. We're in pursuit of fusion, but doing other things along the way, and it's a multi-trillion-dollar opportunity, so something to take a close look at. So I stepped into the business 18 months ago with a particular mission, which was to commercialize the technology and prove that fusion companies can be commercial now, and I'm happy to say that we have achieved that mission. So we're selling capability into defense, space, and high-end materials science sectors. Our absolute specialism is shock physics, so high energy physics. How do you shape and manipulate shock waves to create the most extreme conditions on the planet? So our customers are customers that value extreme conditions, particularly extreme pressures. The amplifier is a platform technology. It's a physical article. I have an example here. I'm happy for somebody to come down and hold it afterwards. I'm not going to pass it around the room because it's very valuable and it's very sensitive, but inside this precision engineered device, there's numerous layers of cleverly shaped materials, micron level accuracy that create these extreme pressure conditions. This is a big amplifier. They can be as small as my fingertip, but just to benchmark, the pressures that we create with these devices in a concentrated way are multiple times a nuclear explosion. So this is really extreme physics. Hence the types of sectors we're playing into. It's consumables models. This is completely vaporized in the process. So use once and have to buy another one. So that's a pretty good business model. But it is precision engineering, and it's born out of incredible understanding of data science and some super sophisticated modeling. But we are a fusion company, so we are still pursuing that fusion opportunity with our own scheme. I may have a similar video challenge in a second. Oh, there we go. So this is the amplifier. Shockwave impacting the top end. It rattles through the device, experiences multiple complex interactions, but your objective is to achieve a peak, highly intense output that's very precise, that enables you to, in a fusion context, compress a fuel pellet to create a fusion reaction, and again, or in a material science experiment, to put a material into its most extreme fundamental state where it behaves like a liquid, and you can understand its behavior. So yeah, really clever things. This is the company on a page. We do super complex modeling simulation, as I said, 50 parameter optimization problems routinely. So we run thousands and thousands of simulations. We have our own data center on site, our own high performance compute capability. We have a manufacturing facility that's 5-axis machines, including the Kern machine, which is one of the most accurate in the world. We are manufacturing to micron level accuracy on very small devices. And we have unique, in private hands, test facilities, 2 hypersonic gas guns, as long as this room, that fire projectiles at high hypervelocity, 15,000 miles per hour, into targets or amplifiers to start the shock interaction, and 2 pulsed power machines. That's a pulsed power machine. In the bottom picture is as large as this lecture theatre. That creates a pulse of electrical power that goes to the center of the machine. So it's taking energy stored in a large volume and compressing it in space and time. So it takes a pulse of electrical current into something, an area the size of my fingertip, and that process means we generate the electrical power of the entire US national grid for 1.5 microseconds. It's just an indication of how extreme fusion is in terms of physics. We have to create that amount of power to get a fusion reaction from a fuel pellet. But it's an incredible piece of kit, very versatile. We can also create solar flare environments, the most extreme solar flares, and you can do interesting things with the electromagnetic forces that are generated with the US national grid's worth of electrical current. So we do a lot we spin around that loop every single day. So from the modeling to the manufacturing to the testing and close that loop. So we're able to create really valuable test data for ourselves and for other customers. And when we need to, we go elsewhere. So we particularly go to the US. This machine in the top is now a machine that's 10 times the size of this room. It's the largest pulse power machine in the world in New Mexico. And that's 10 times the world's electrical capacity, 10 times the world's electrical capacity. When they fire that machine, it registers as an earthquake. And we take our tiny amplifiers, tiny ones, so 10 times smaller than this one, into that machine, and we create the most extreme pressures that have ever been achieved over in New Mexico. The colourful chart, I won't go into any too much detail, but it's time along the bottom from, I think, 1980 onwards, pressure up the left-hand side, and it illustrates my point from earlier. The grey bubble, if you can see it, is the pressure achieved in an underground nuclear weapons test, and it's 2 terapascals or 2,000 gigapascals. The colourful bubbles are national laboratories in the US that were designed and built to replicate those conditions, because a treaty was signed saying we should no longer test nuclear weapons underground. And they are now achieving multiples times the pressure of a nuclear explosion. And then on the right-hand side, this is First Light in Oxfordshire. So we're able to get close to the conditions that are achieved in multi-billion-dollar premier facilities in the US, where it costs $1 million an experiment. And you may have to wait 2 to 3 years to get a test slot. We're able to do that every single day in our facilities in Oxfordshire with strategic partners, Atomic Weapons Establishment, key universities, NASA, and that particular machine is owned by Sandia National Laboratories, who have been a partner of ours for 3.5 years. So yeah, again, extreme stuff. So in a fusion context, this would sit at the heart of our fusion scheme. So in the chamber, it would be the initiator for the fusion energy reaction. So it's a smart fuel, effectively. That's the simplest way to think about it. And in a fusion power plant, you'd be consuming millions of these per power plant per year. It's a repetitive pulse process. The fuel is consumed on every shot, the goal being to achieve a high gain reaction. You need to replace the fuel, you need to recycle materials that have been destroyed, and you need to remove, obviously extract the energy as part of that process. So our scheme that we launched last year is called FLARE. It's fusion via low power assembly and rapid excitation. The key feature being low power. There's a huge number of technology solutions for fusion, many of them over in the US. And in the US, they're building some of the biggest machines on the planet, extremely high power, massive machines, which is one way to go. And similar thing is happening in China. We believe in low power, but you can only use low power if you can get that extreme reaction of the fuel. So our target technology is intended to generate a gain of 1,000, so 1,000 times more energy out than in a fuel capsule, which has the potential energy of more than a barrel of oil in something that's 1 millimeter in diameter. So we're on a journey to prove that, and that would sit at the heart of the plant, and then you've got to engineer the plant around that. The other benefit of a high gain reaction, and again another benchmark, the current world record gain is 4.2, created in a facility in the US using 192 high-powered lasers. This is targeting a gain of 1,000 at the fuel, so that's 30 to 40 at the total power plant level. But if you get high gain, then you have to repeat that process less frequently. So not 10 times a second, not once a second, but once every 15 to 20 seconds. So it makes the whole engineering of the power plant far simpler. It enables you to dial in known technologies and capabilities from fission, from automotive sector. It is a repetitive process, as I've said multiple times. There's an automated system needed to get the fuel in, to recycle the materials and to extract the energy. But it's absolutely feasible to do this in relatively short order. The brief I set my fusion team was keep it simple, no new physics, utilize as much engineering expertise as possible from other sectors, and let's bring this together. So our play in fusion, First Light's play, is to be the target company, the fuel target company, and then build these reactors in partnership with engineering companies and other innovators. So we're on a journey now to build the first of a kind, which would be monetized. So it would do fundamental science experiments, it would do defense experiments, experiments for the space sector, and also fusion work. So from day one, you can monetize that facility, and then it's scalable beyond that. And just picking it apart a little bit more, we need, there's many things you can poke at in inertial fusion as challenges, and we've gone on a conscious journey and made a serious effort to knock those things down. So we know we can do robust targets. They're proven in our facilities and in the most extreme machines in the world, in the US. We know that if we can get the high gain reaction, the driver becomes far simpler. A low power driver is, we can do that today, they exist today. We would integrate a laser into this scheme, but it's known laser technology. We need expertise around the chamber. This is a dramatic reaction. This is releasing up to 10 gigajoules of energy on each shot. So we need a robust chamber that will be filled with lithium. We need an automation system to drop the fuel in and enable that shot to take place and then to be extracted and replaced. And we need the fuel cycle to be designed. Actually, one of the big opportunities in fusion, the huge opportunities, is around the fuel cycle, from the supply of particularly tritium through to the recycling of some of those valuable materials that go back into the fuel cycle. I think that's a huge opportunity for the manufacturing sector, for the engineering sector more broadly, and whoever controls the fuel will control a large piece of the fusion market. So watch this space. We're really on a charge now. We closed a funding round earlier this year, including support from the UK Atomic Energy Authority and from private investors. We've been entirely privately funded up to this point. But there's real engineering there today, including our own machine. I'd invite you to come and visit, maybe not all at once, but we've had about 60 people through the facility, I think. This is an incredible machine, second largest pulse power machine in the world, equivalent of the entire US national grid in terms of current, but needs to be bigger for a fusion reactor. But the knowledge is there to design, build, and operate these things. And I just welcome your leaning in with a partnership mentality, because I do think the industry is going to go on a serious collaboration journey in the next year or so. So thank you very much. Thank you.